So here are a couple more transition metals I want to talk about. But remember, any transition metal could be used as an example, folks. To organize ourselves, we focus on period 4 transition metals. But do not be alarmed if you see other transition metal examples, like silver, our soft, ductile, malleable silvery metal, right? That's going to get its name from the Anglo-Saxon word sulfur, okay? And that's kind of how it's able to kind of go from basically Anglo-Saxon and a little bit of Latin from the word argentinum, right? Which is how it kind of got its AG portion. So what you'll see with a lot of these different elements, and sorry for me butchering all the names, is that you kind of are mixing different ways of the actual element coming about or the words that are actually used. Based on the element symbol and the name itself too. Also, sometimes the common name can make things a little bit more confusing. Now, what do we use silver for? Silverware, tableware, dental fillings, mirrors, jewelry, all kinds of things. Next, we can also talk about good old gold. We see gold in jewelry. We also see it in dental fillings. We also see it in gold teeth, grills, luxury watches, artwork, architecture, coins. It's very soft and malleable. It's yellow metal. It's going to come from the Anglo-Saxon language again. Okay, which is going to come from its actual chemical symbol because it comes from the Anglo-Saxon word aurum, which is like the shining dawn. And so that's just little things that you don't have to remember. It's just things that helps you kind of associate yourself with some of these transition metals. We also can talk about zirconium, for example. Zirconium is going to be a tough, silvery, corrosion-resistant metal. So corrosion-resistant, that means it's going to be good for any kind of alloys. And it's actually used for alloys or mixtures of metals for aircraft components. You also can see it in dental implants and can be found in some gemstone. We also then have you can also see platinum, and again, other transition metals as well. But platinum is going to be a very heavy, soft, malleable, and ductile silvery white metal. Okay, folks, it's going to come from the Spanish word platina, which means little silver, because it was first known as an unworkable silver-like metal, which was found along some gold deposits until people start realizing its value. Okay, folks. We'll see we'll see platinum in a lot of jewelry, medical implants, fuel cells, catalytic converters, like we were talking about before. We're using it as a catalyst and the catalytic converter of a car so that it basically can never, ever be getting rid of because it never breaks down at all. Okay, folks? So for example, we're going to use that platinum in that catalytic converter just to make sure that the car that you're driving doesn't continue to give out harmful emissions. That's kind of what it controls. So having a substance like platinum in there that's not going to break down, right, because it's not used up in the chemical reaction, is almost perfect. So we're literally converting that gas to less toxic compound. Then we have those inner transition metals, folks. So what about those? We cannot forget about them. The lanthanides and the actinides. They're going to be our F block, right, on the periodic table. So here, we're going to see the F block transition transition elements that we're talking about here. So the lanthanides are going to be in period 6. They're also called the rare earth elements, while the actinides are going to be in period 7. Okay, and they're all going to be radioactive and have very similar physical and chemical properties, which is really cool because a lot of times we're talking about how sometimes they don't, but we do have groupings like with the actinides where they do have similar physical and chemical properties. Now, when it comes to both lanthanides and actinides, they do like to have form stable compounds with the +3 oxidation state. And I do want to give a couple of examples for each. So the lanthanides are really good as catalysts in various industrial processes like petroleum refining, for example, medical imaging, like MRI scans, nuclear reactors that are going to help us basically, not really the nuclear reactor itself, but the structural materials of it. And then actinides, for example, are really good for material scientists. So because they have such unique properties, they're all radioactive and stuff like that, they actually have huge applications for advanced materials. And so sometimes are high temperature materials, and sometimes people are studying those as well. And nuclear weapons, of course, because they're radioactive, and space exploration. So some of the probes that are actually in different satellites or just like on different planets, for example, they're actually using plutonium and things like that, portions of the actinides, to actually be able to explore space. So there's going to be a lot of uses for some of these lanthanides and actinides. Of course, we don't go into all the details, but they're pretty cool to know. When it comes to transition metals, right, we talked in the beginning a little bit about how to extract these transition metals. So we start off with some kind of ore, and this ore has pieces of the transition metals or different minerals that we want to extract out. And then once it's extracted out, we kind of create a pure form of it, okay? So there's going to be various information on how to extract these transition metals from their ores, but you're not responsible to know the details. So an ore is simply going to be, again, a naturally occurring material that has these variable materials within them, these minerals or these transition elements, for example. And of course, we want to extract them because they can be highly profitable. And what do we mean by that? Look at all the different industries we can use them for. So because of that, we just know that once you have extracted a pure amount, you can get a good amount of money. And then, of course, we can go further and say, when we're talking about purification or getting different organic compounds as well, we know that we can get things like fuel or gasoline from these type of processes too. We're just sticking to the preparation of transition metals. The goal is that you're first going to gather all of your materials. This is just an example of getting copper, for example, and then you're going to smelt it. Smelting means that you're going to heat it up and you're going to extract the metal from the ore itself. Now, sometimes there's a lot of byproducts of this, and those byproducts can be used too. You can use a byproduct here of the copper for like steel making, for example. But no matter what, the metal that you obtain from smelting is very, very impure. And because of that, you want to make sure that you're creating the most pure product. Just like in lab, when we do recrystallization, we heat it up again. So sometimes you'll have a process of refining where you have to heat up the metal again to release impurities. A lot of times you'll also see like electrolysis where they use electric current to remove impurities, whatever it takes to get to that pure product. And sometimes those processes are a lot of money as well. So the entire goal of having that ore, starting off with that ore, smelting it down, and then refining it, allow you to have so many parts for boats, different steel mills, all different things that we use in industry. And of course, we can go further to different processes like nanotechnology and things like that as well. Okay, folks? So again, you do not have to know the details of preparation of transition metals. Just know that it exists, and as you go along in chemistry, then of course you will be seeing this in higher up, well, in different courses that you go up that are higher in. Okay? And again, more cool stuff to learn about these transition metals. Now, finally, how do we put all this together, folks? We talked about general properties of transition metals. Okay, we went through that. We made lists of them. We got to be able to explore some of the actual properties and examples of the different transition metals we see as our models. Now we're going to go in deeper into a little bit details about those atomic, physical, and chemical properties. Okay, folks? So how does electron configuration differ with transition metals? Is it the same as nonmetals and metals, or is it different? We'll see it's different. Okay, what about the trends that exist? So we're talking atomic size, ionization energy, electronegativity. What kind of trends exist specifically for transition metals? Again, folks, the goal is that we're organizing ourselves and telling ourselves we're learning completely different block on the periodic table. No more main group elements for metals and nonmetals. Now we're dealing with transition elements, and we have to kind of learn about all the different properties that exist specifically for them. Okay? And then, of course, we can even go further and talk about those chemical properties like oxidation and reducing strength, okay, or color. How these model transition metals become reactive. We get to explore all this and kind of go a little bit further as best as we can in the boundaries of our course in this lecture. So let's go ahead and get into it.